This is a short video about total differentials, and it builds on the previous video on partial differentiation and represents really a sort of application of the idea of partial differentiation. To get the idea here, let's write out a function y that depends on x and z, two independent variables. And we want to define the total differential of y, and that's written dy. And the total differential of y is defined this way. It's defined as the partial derivative of f with respect to x, the first variable, times a small change in x denoted by dx, plus the partial derivative of f with respect to z, the second variable, times the change in z, which represents a small change in z. So these constants here, dx and dz, represent small changes in the independent variables x and z, and we can find out what the change in y is in this function by means of this formula. Now, some people use a little bit different notation. For example, one of the things they write is, instead of the whole set of scripts there for the partial derivative of f with respect to x, they write f with a subscript of x times dx plus f with a little subscript z to denote the partial derivative times dz. But notation aside, the idea is exactly the same and conforms to the definition of total differentials. Now notice, first of all, that if y is a function of only one variable x, and we compute the total differential dy, that's equal to the partial derivative of f with respect to x dx, so that we can divide both sides by dx and come to the not so startling conclusion that the derivative of y with respect to x is the same thing we defined earlier as the partial derivative of the function with respect to the variable x. So let's use this knowledge to work out a simple example or two. For example, suppose I had a function y that was equal to 2x squared z minus 3x z squared. And I wanted to find the total differential of the function. That is, I wanted to find dy. Well, we know from the definition immediately here at the left that that's equal to the partial derivative of the function with respect to x, which is 4xz minus 3z squared multiplied times the small change in x, plus the partial derivative of y with respect to z, which is 2x squared minus 6xz times dz. It's also, using the total differential is a very convenient way to differentiate what are called implicit functions, functions that might be written this way: 0 equals f of x and z. If we want to compute the derivative of x with respect to z, that looks like, if you can't actually solve this equation for x in terms of z, a difficult or maybe even impossible task. But the total differential finds a way to do that. Computing the total differential of this function, we can compute the differential of x, or the partial derivative of the function f with respect to x dx, plus the partial derivative of the function f with respect to z dz. And then we can solve that function, and we'll find that dx is equal to partial derivative of f with respect to z divided by the partial derivative of f, and a minus sign out here, of f with respect to x times dz, so that if we then find dx over dz, that's equal to minus the partial derivative of f with respect to z divided by the partial derivative of f with respect to x. And because we can compute those partial derivatives very easily, we find out that this is just the derivative of the implicit function taking the derivative of x with respect to z.